Mr. Cook again. So today's lecture, reading, and quiz is going to be about the photoelectric effect. This is essentially solar energy that is a very, very hot topic today. So we're going to talk about the photoelectric effect. And what it represents is a dual nature in light. People think of light, or physicists now used to think of light as just a wave, like a mechanical wave, part of the electromagnetic spectrum that we studied before. But we also discovered it will act like a particle being like a chunk, like a little electron. So we're going to understand how that was. Albert Einstein did a lot of work on this, along with Bohr, and along with a ton of scientists. So we're going to see how we go on this. As I mentioned before, we talk a lot about solar power. Big issue today, putting up solar arrays. We use it to power stuff in space. El Paso's the Sun City. A lot of places are looking at putting up solar cells to supplement stuff, especially with problems, like in California where they keep losing power. Here where the power grid is getting a strain because of our population, maybe solar is a possibility. What we call the photoelectric effect and the particle nature of light. Albert Einstein came up with the idea that light could be described as a quanta of energy. You should remember previously we learned a quanta is the smallest little packet of energy. It's essentially what we usually think of when a little electron jumps suddenly in another orbit. It doesn't slide over, it just moves over there. We have our electron, boom, it's in the next orbit. And it has zero mass, kind of freaky, we can't weigh it, which makes kind of the math seem a little different. But that's what we're talking about. We're talking about a chunk of energy that is moving when we talk about a particle. The energy of that photon, as we learned before, is quantized. And we learned the equation, energy equals Planck's constant times its frequency. The V stands for frequency. And up to this point, we always thought of light as a wave. Like when we played with our springs, we would see it as a wave. It moved up and down, it would hit something and bounce off. We started seeing it in packets, quantum packets, as a particle. And by doing experiments, we can decide to measure it as a wave, and wow, it works out. We can also measure it as particles, and wow, it works out. So the experiment shows it's both. Many old physicists will still argue this. This is kind of an area of discontent. So what's happening is when I shine a light onto a chunk of what we call photomagnetic metal, this is just an example, or in many cases that's what builds up a solar cell, is photomagnetic. If a light is shined on it, and remember the light coming from a source, from the sun or something else, that's the incident light. What it does, it frees the little electrons that are on it, and it causes them to spring off, causes them to move in quantums. If you remember in electricity, that's what a current flow is, it's moving electrons. So that is essentially what we're starting. Now, only certain materials use this. I can't just shine it on any chunk of metal. It has to be what we call a photosensitive metal. Luckily, there's tons of them out there. It's also a good investment for the future if you are into the stocks. The way it works, hold on a minute. Beep. Does we see that? So the way it works is light will hit photosynthetic material. It causes electrons to flow. We would often do this by putting the materials in a vacuum, so we just get the electron flow. As it hits, these electrons we call photoelectrons. They're bouncing off. And they would move as they get going. We get a positive charge in the anode. The anode is the positive end of a battery. and it will move to the cathode, the negative end of a battery, because we have a potential difference. Remember, electricity is a potential energy. As we charge the plates in a battery, the electrons want to move from one positive to the negative, is how we think of current flow. And by hitting light onto a photosensitive material, especially if we put it in a vacuum as a tube, or we can cause the current to move. We can measure it. We can also use it to charge up batteries. Most of what we call solar energy is used to charge batteries. It's not actually directly powered from the little solar strip. Not always. We do power lots of things from this. Remember, light comes in different frequencies in the electromagnetic spectrum. And certain frequencies work better. There's a sweet spot. And depending on the material we were using, will depend, essentially, think of which colors are going to move it. Which colors cause the electrons to move. There's also what we call a threshold. If we come back to here, red would sort of be one threshold, high frequency, long wavelength, to the ultraviolet. There is a starting and stopping point where it will go. If the color is too low, we're thinking once again of wavelength and frequencies of colors, it doesn't turn on. It needs think of it as a certain speed to get going. If it gets too high, it also shuts down. So there is a sort of sweet spot. This is sort of illustrated here. The red light causes nothing to go. Around the green is where it gets moving. Around the ultraviolet is its maximum number and its maximum speed. And we can use that in the calculation. Here's what also is kind of cool, what they find kind of weird. It seems to be based on the frequency of the light, not the intensity. If I shine a brighter light, most of the time we think a brighter light is going to make it move faster because it's providing more energy. That's not true. It has to do with the color and the frequency. If I'm sitting here with red light, I can use super, super, super bright red light. It's not going to go because it's red. Near the end of the violet, it is the same thing. Even if I make it higher intensity, really crank up the light so it seems super, super bright, it's going to be at the same speed. It's based on the frequency of the color, not the intensity of the light. So this minimum frequency is what we call the threshold. Threshold is sort of where something starts. And when it hits the threshold frequency, what it is it starts releasing the atoms, or the electrons. We call that it has reached the part where it breaks the binding. Think of binding as glue. If I can break the binding, my little electron can pop off. That's all that it's talking about there of the metal. And once again, that is based on a frequency, not an intensity. Now, classical physics, where we thought of light as just a wave, had trouble explaining this. Because we would think eventually it would get enough metal and eject. It didn't. Even if the light was at a full frequency, nothing happened. So by our understanding of waves, this experiment, we couldn't figure it out. Einstein started coming up with the idea of the particles. And that's how he would explain the photoelectric. Instead of talking about light as a wave, by thinking of it as packets and as particles, this is how he could explain how we got the photoelectric effect. In other words, how if we hit metal with certain colors, it will cause electron flow. And he came up with what we talked about before. We have a threshold color. Above the threshold, it will start going. As the frequency gets higher, it will eject with a higher speed. Again, based on the frequency of the colors, not on the intensity. There's a simulation here. This comes from the book. You are welcome to go with that. You have to find a computer that it works on. But it's kind of fun. You can actually see by changing frequencies, you can see how the speed of ejection works. Now remember before, when we were talking about quantum, we had our energy equals Planck's constant multiplied by frequency, E equals hv. Well, we're going to use this again. Remember Planck's constant, 6.62 times 10 to the minus 34. And by looking at it, and what it essentially tells us is E would be the minimum energy, in other words, the threshold. So I can use it to calculate that. Notice it is based on frequency, the V, not on the intensity. So if it is below, if I have a set number for my energy that I know will work with this metal, if my V is too low, I'm not going to get the energy. If it gets higher, I will eventually get to the part where it will start ejecting and its speed will go up. I can tell that. And then a spot where it just sort of stops. It hits its maximum things. We use this idea to create photoelectric cells using the photoelectric. As I've showed you before, we have the cell. We put it on all sorts of stuff. Usually it's to charge batteries, but we'll often use it in stuff like calculators. Has a little solar cell. This goes directly into the display. That's why we can't use these in the dark. And since it is moving, the chapter ends up a little bit by talking about kinetic energy. Remember, kinetic means moving. So the kinetic energy is the movement of the photoelectric things. What that means is, since we have velocity, as the velocity will go up, the kinetic energy goes. Remember, we do have a threshold, a certain spot where it starts based on frequency and a spot where it's kind of the maximum based on. What we have learned by looking at the formula is as the light goes up and as our maximum speed is reached, which is the maximum kinetic energy, it increases linearly. Remember, line. So it increases in a nice, neat graph like that. It's not one of those wacky curve things we throw at you in calculus. If the intensity is increased, it should release more electrons. But what's kind of weird is it releases electrons, but it does not increase the kinetic energy. It just increases the speed. So Einstein came up with this idea that essentially says the incident light, the light I'm shining out of the photon, calculates how much is required to eject it. What we've been saying over and over again. He discovered, this is kind of a rephrase of everything, but this is more from the words of Einstein. If the frequency is increased above the threshold, it will start going. What happens is the electron on the metal absorbs that energy. So this electron is starting to get a little more energy, and then eventually it ejects after it got enough quantum of energy, and the energy will free the electron. Once the electron is free, it can flow and we will have a current. The remainder of energy that is not used for the ejection just goes into the speed and helps it go faster. We learned that too. Higher frequency, higher speed. So in summary, the two big things we got there is we can look at light two ways. We can look at it as a wave, and we can look at it as a particle in terms of photons. To understand how photoelectric effect works with metal to eject it, we tend to stick with the idea of looking at it as a particle. Earlier in the class, when we were reflecting lights off mirrors of that, we were looking at it as a wave as part of the electromagnetic spectrum. So, however we want to study the light or the effect, helps to pick one or the other. The photoelectric effect is produced by the light strikes the metal, fills the electron with energy, causes the electron to eject, and once it's ejected, we now have a current flow. Any questions? Remember, this just supplements the reading. The questions will come from the ebook online, and then you have the quiz online. Enjoy. Welcome to the world of solar energy. This is just your introduction.